Let's talk about the rank of a matrix. We've seen that the column space of a matrix A is the set of linear combinations of the columns. In the same way, the row space of a matrix A is the set of linear combinations of the rows. We denote the row space of A by this. Just call it row A, row space of A. Find bases for the row space of A, the column space of A, and the null space of A, where A equals this matrix. Here's how we do it. Elementary row operations do not affect the row space. So let's find the row echelon or reduced row echelon form of A. The non-zero rows form a basis for the row space of A. Here's the reduced row echelon form of A. The non-zero rows are this, this, and this. Therefore, since those are the non-zero rows of the reduced row echelon form, those are going to be a basis for the row space of A, just those three vectors. You can also write them as column vectors in this way. Now, I did it with the reduced row echelon form of A. We could just as easily have done it with the row echelon form of A. That would have been fine. Now let's find a basis for the column space of A. Recall that the pivot columns of A form a basis for column space of A. The reduced row echelon form of A is this. We've seen that before. These are the leading variables. Therefore, those columns are the pivot columns. So these are going to be the pivot columns of A. And the pivot columns of A form a basis for the column space of A. Therefore, the column space of A, or I should say a basis for the column space of A, looks like this. Now notice, we want the pivot columns not of the reduced row echelon form, but of the original matrix A. Those pivot columns will be a basis for the column space of A. Now let's find a basis for the null space of A. The reduced row echelon form of A looks like this. Using the reduced row echelon form, we find that, okay, so again, this first equation is going to be x1 plus 3x3 minus 6x5 equals 0, because we're trying to solve ax equals 0, and this is the reduced row echelon form of A. We also get x3 minus 20x5 equals 0, and x4 plus 8x5 equals 0. Now, if we write these three equations, which we saw in the previous slide, as parametric vector form, this is what we end up with. Move the free variables to the other side, and we end up with x1 equals negative 3x3 plus 6x5, x2 is 20x5, x3 just equals 6, x3 just equals x3. That's what we do with the free variables. x4 equals negative 8x5, and x5 equals x5. So we can pull out the x3 and the x5 and write it like this. Notice that a basis for the null space of A is just going to be these two vectors. And that's because any vector that's in the null space of A can be written as a linear combination of these two. Therefore, that's going to be a basis for the null space of A. They span the space, null space of A, and they're linearly independent. The dimension of the column space of A is called the rank of A. We denote this uncreatively by rank A. What's the dimension of the column space of A? That's going to be 3. Here's why. Because we saw that a basis for the column space of A has 3 vectors in it. Therefore, the dimension of the column space of A is 3. That is, what is the rank of A? That's also going to be 3, because the dimension of the column space is what we call the rank. What is the dimension of the row space of A? That's also 3. Here's why. Because when we found a basis for the row space of A, we found that it had 3 vectors in it. Therefore, the dimension of the row space of A is 3. So notice, the dimension of the column space and the dimension of the row space are both 3. Coincidence? I think not. It's always true that the dimension of the column space equals the dimension of the row space. Here's why. The non-zero rows of the reduced row echelon form of A are a basis for the row space of A. Okay, we saw that earlier. This row, and this row. Each of these rows corresponds to a leading variable. Okay, this one, this one, this one. So, the number of leading variables, namely 3, equals the number of non-zero rows in the reduced row echelon form of A, equals the number of vectors in a basis for row space of A. All of those are going to be 3. Similarly, the pivot columns of A form a basis for the column space of A. This is A. Okay, so we know these are going to be the pivot columns, or really, these are the leading ones, and they correspond to pivot columns. So that means we've got 3 pivot columns. That's going to be a basis for the column space of A. Each pivot column corresponds to a leading variable. So the number of leading variables, namely 3, equals the number of pivot columns of A equals the number of vectors in a basis for the column space of A. So notice the number of leading variables equals the number of vectors in the row space of A, and the number of vectors in, I should say the number of vectors in a basis for the row space of A, and it also equals the number of vectors in a basis for the column space of A. What is the dimension of the null space of A? That's 2. Here's why. Because when we found a basis for the null space of A, it had 2 vectors in it. But actually, we didn't even have to go through all this rigmarole to calculate the null space of A to know that the answer is 2. The dimension of the null space of A is called the nullity of A, or nullity A. There's a connection between the rank of A and the nullity of A. Let A be an m by n matrix. Then the rank of A plus the nullity of A equals n. Here's why. There are n columns. It's an m by n matrix, which corresponds to n variables. Each of the n variables is either a leading variable, that means it's counted in the rank of A, or a free variable, that means it's counted in the dimension of the null space of A. So all of the n variables are either in the rank or in the dimension of the null space. That means when you add together the rank and the dimension of the null space, you get n, the number of columns, because variables either have to be leading variables or free variables. Let's fill in this chart. Oh goodness, we have these 4 matrices, and here's some information about them. We can do this. The dimension of the row space of A is always equal to the dimension of the column space of A. We saw that earlier, so this must be 4 as well. The dimension of the null space of A, we saw a moment ago that when you add together the rank, the dimension of the column space, and the number of free variables, the dimension of the null space, you get the number of columns, 4. So again, the rank is 4, and when we add to that the dimension of the null space, we should get the number of columns, 4. Well, obviously this is going to be 0. So the dimension of the null space is 0. The nullity is 0. Similarly, if the dimension of the row space here is 3, the dimension of the column space also must be 3. And 3 plus what is going to be 4? 3 plus 1 is going to be 4. So the dimension of the null space of A is going to be 1. If we have a 5 by 8 matrix, switching it up on you, hope it doesn't confuse you. If the dimension of the column space is 2, that means the dimension of the row space is going to be exactly the same. That'll be 2. And 2 plus what equals the number of variables? 2 plus 6 equals the number of variables, the number of columns. Therefore, the dimension of the null space of A, the nullity of A, is going to be 6. If we have a 9 by 6 matrix, oh man, rocking your world, not telling you the dimension of the row space and the dimension of the column space, telling you the dimension of the null space. The dimension of the null space of A is 5. 5 plus what is going to be 6? 5 plus 1 is going to be 6. So those are both 1. We can add some statements to the invertible matrix theorem, that monster theorem that we've been looking at that seems to have 1,000 statements that are logically equivalent. Let A be an n by n matrix. The following statements are logically equivalent to the statement A is invertible. The reduced row echelon form of A is the n by n identity matrix. Okay, we've seen some of these before. We've seen many of these before. A has n pivot positions. Ax equals 0 has only the trivial solution. The columns of A are linearly independent. The columns of A span Rn, etc., etc., etc. One that we added recently, this wasn't part of it initially, but we added it a little later, is the determinant of A does not equal 0. Okay, that's logically equivalent to all the above ones. Here are the new ones. Okay, so the statement A is invertible is logically equivalent to the statement A transpose is invertible. Why? Well, A transpose is invertible if and only if A is invertible. That's because A transpose inverse equals A inverse transpose. In other words, A transpose has an inverse if and only if A inverse exists. And similarly, if A inverse exists, then A transpose must exist. So A is invertible if and only if A transpose is invertible, which means that all the statements we said about the columns are also true of the rows, because the columns of A transpose, or the columns of A, are the same as the rows of A transpose. So if the columns of A are going to be linearly independent, if and only if the rows of A are linearly independent, We can also add these statements to the monster theorem, this invertible matrix theorem. The columns of A are going to span Rn if and only if the rows of A span Rn. That's going to be true if and only if the rank of A is n. And the columns of A are a basis for Rn. The rows of A are a basis for Rn. Those are other statements we can add. It's in the invertible matrix theorem.